Okay, so welcome everyone. So today it's my pleasure to welcome Yuanzhao Zhang, who will be talking about Catch-22s of reservoir computing. Yeah, thanks.
Okay, thank you. And thank you everyone for coming. So yeah, today I'll be talking a little bit about reservoir computing and the next generation reservoir computing. So I want to, okay. So I want to start my talk kind of in the 1600s. The legend has it that Newton was sitting under a tree, down came an apple, up came Newton's law for universal gravitation. But not everyone is as smart as Newton. I know I'm not. So it'd be nice if we can have some kind of algorithm that can automatically turn data into some kind of physical law or governing equations. And this has been the dream that has been driven the field of, machine learning for dynamical systems for a while now. In my mind, there are kind of two major camps of methods that are trying to realize this dream. The first camp is kind of very close to Newton's approach, which is trying to look at the data and then try to come up with some kind of parsimonious description in terms of, say, differential equations to describe the underlying system that can best explain the data and predict the future. So many methods along those lines uses techniques such as sparse regression, genetic programming, symbolic regression to try to come up with a parsimonious equation that would explain data and generalize well to unseen conditions. But of course, in many other cases, we don't care too much about having a parsimonious description of the system. And in many cases, such as in climate modeling, we simply cannot have a simple description. So in those cases, we often still want to be able to predict the future. I want to know where it will rain on me in 10 minutes, or how would the climate be like in 10 years. So there are a lot of other approaches that are usually based on neural networks that are trying to build a surrogate model of the underlying system and try to make forecasts. So there are techniques such as reservoir computing, neural ODE, neural operators, things like that. And in my mind, when I think of those methods, I try to put them on a spectrum. On the left-hand side, we have those really large neural network-based models that are more expressive, but also require more data, needs more computation. They have less inductive bias built in and are usually less interpretable. And on the other side, we have those more physics-based approach that are usually less expressive because we have more inductive bias built in, but it also requires less data, less computation, and can often be more interpretable. So, we have some examples that I'm just putting very imprecisely on this line. And of course, because of those differences on the left-hand side, for those very large models, because we have those kind of composition of nonlinear features, activation functions, we can choose them somewhat arbitrarily. Whereas on the right-hand side, we really need to choose our nonlinear features as well as the coordinates they are expressed in very carefully and wisely in order to have a good performance. So in this talk, I mainly just want to use the reservoir computers and next generation reservoir computers as an example to demonstrate this trade-off. Okay, so what is reservoir computer? I don't need to introduce too much to the audience here, but just for completeness. So let's see. So a reservoir computer's basic idea is we want to use some kind of random high-dimensional dynamical system to emulate the dynamics that is being learned. So in particular, we have this random reservoir, which usually have, say, thousands of nodes in it and have fixed random coupling between them. And this is the dynamics of the reservoir. So R represents the state of all those nodes inside the reservoir. They have interaction among themselves, which is described by this matrix A, which is fixed at the very beginning and it never changes. So X is our training data. So we use this training data to drive our reservoir through this input matrix B, which is also fixed. And then we have some bias D. And we apply some nonlinear function, which, for example, sigmoid, to this state element-wise, and this would be the dynamics of our reservoir. So more graphically, we have, say, data generated from a Lorentz system, and we use them to we map this low dimensional time series to a high dimensional driving through this matrix B, and we use to drive our reservoir. And then we want to map it back down into 3 dimensions using this output matrix W, which is the thing that we're going to train. And our training objective is we want this W times RT to be as close to the original time series X as possible. So because we're only training the output weights W, this is a much simpler optimization than what people do in traditional recurrent neural networks. And after training, during prediction, we simply close the loop, meaning we replace the training data X by our internal reservoir state, basically W times RT. So with that, we get an autonomous system that can keep going and predict the future, hopefully. So this is a continuous formulation of the reservoir computers. There's also a discrete version, which is probably more popularly utilized in the literature. So again, we have the reservoir state. Now instead of a continuous system, now it is a discrete map. So we are trying to use RT to map RT to RT plus 1. And again, we have the connection among the reservoir nodes, and we have the input matrix, we have the driving signal, and we have a bias. And again, we want this W times the reservoir state to be as close to the training data as possible. And this is just a simple linear regression problem, and it is a convex optimization problem. So you can get an analytical solution and calculate them very easily. And again, during the prediction phase, we turn the reservoir into an autonomous dynamical system by replacing the training data XT with W times RT. So as in terms of benchmarking the performance of reservoir computers, I think in the past literature, what people have done the most was to use those very well-established chaotic dynamical systems, such as Lorentz systems, and Komoto-Sierpinski equations. And those systems, they all have a single attractor. So just to change things a little bit, here we want to test the performance of reservoir computers using multistable systems, which is very common in practice, from gene regulatory networks to to differentiating cells, to power grids, and even for neural networks themselves, of course. So can reservoir computers learn basins of attraction in this context? And for this purpose, we're just gonna use a very simple toy model, which is basically we have a flat surface, say a table, and we place 3 magnets, which is shown here, equilaterally on the table. And then we hang a hang a magnetic pendulum from the ceiling, and we release the pendulum somewhere, and then it will wander around and would eventually be attracted to one of the magnets. So this is an equation describing the system. X and Y are the coordinates on the table, and omega naught is the natural frequency of the pendulum. This term describes the dissipation in the system, say due to air friction. And this nonlinear term comes from the magnetic force interaction between the pendulum and the three magnets. So of course, it's a dissipative system, so it would eventually settle down to a simple fixed point attractor. In our case, it would be one of the three magnets. Usually when people train reservoir computers on those typical chaotic systems, they would usually discard the transient dynamics because they want to learn the chaotic attractor. But here, because we only have simple fixed points, the transient dynamics is actually all we have. So we need to utilize those transient dynamics for our training. And interestingly, this system actually have a very rich transient dynamics, which is kind of chaotic. And as a result, you can have quite complicated basins of attraction for this system. So here, the three white dots are the three magnets. And the color represents which magnets would the pendulum go to if starting from that initial condition. So the red initial conditions would all go to the red magnet, and the same for the black and the blue ones. However, I should emphasize that, we can. This is not true fractals. If you zoom in enough, the basins are not fractal, and we can actually tune the complexity of the basin, say by changing the height of the pendulum from the table. And finally, this system is interesting also because it has non-trivial nonlinearity in the system, which is the nonlinear magnetic pendulum interaction here, which is different from the usual quadratic nonlinearity we usually encounter in those traditional benchmark systems. So it'd be interesting to see how do reservoir computers do on this system. So let's test the traditional reservoir computers first. So here you can see that here we're actually plotting two curves. One is the real system, which is the prediction from the reservoir computer. And you can see only one curve because the reservoir computer does very, really well. And you can only, they basically overlaps. And so you can only see one curve. But what we need to remember is that because the reservoir computers themselves is also a dynamical system, its prediction can change if we start the reservoir itself from a different initial condition. So there's initial condition for the pendulum system, and there's initial condition for the reservoir computer. That's why usually when making predictions, we want to drive the reservoir computer with the ground truth signal for a while to, say, warm up the reservoir computers. So what you can see here is that if we warm up the reservoir for long enough time, it can perfectly capture the dynamics of the magnetic pendulum system. However, if you only warm up, say, for a shorter time, then the reservoir computer may not be able to go to the right basin of attraction for itself, and it will fail its prediction. So here is a more systematic view of what's happening. So here the y-axis is basically the prediction error for the reservoir computer. And the x-axis is how much time we use to warm up the reservoir. So you can see there's a very sharp transition from the reservoir computer being not able to predict the correct fixed point to it being able to capture the full transient dynamics very well. So the dashed line is actually this panel, and the solid line is this panel. And you can see that, this transition happens right before, we transition from some really chaotic transient to just damped oscillations. So in this sense, the reservoir computer has a catch-22 because you really need to drive the reservoir already close to the correct fixed point. So all that remains is to go there through damped oscillations in order for the reservoir computers to have a good performance. So, RC is great, but it needs to be warmed up properly. So this motivated us to look at more recent variant called Next-Generation Reservoir Computer. So for NGRC, the basic idea is that we want to shift the nonlinearity from the reservoir itself to the output layer. So for traditional reservoirs, the output layer is just linear. It's only determined by our linear output matrix. So for NGRC, what people are saying is, okay, what if we make the reservoir linear and introduce more complicated nonlinearities in the output? Well, because now if the reservoir is linear, then there's actually just no reservoir at all because everything is linear. You can combine them freely. So then what really matters is what kind of output nonlinearity you choose. For example, here is an example of a quadratic output nonlinearity. So you have the state x, xt, yt, zt, and very often you also tag on some delay states. So xt minus 1, yt minus 1, zt minus 1 to kind of build in some kind of memory in the system. So mathematically, it's basically here we have our current state xt. We want to predict our next state xt plus 1. And we do this using all the nonlinearities we have. So basically, we want to use those nonlinear features to help us propagate from xt to xt plus 1. So of course, just to make the notation simple, we can use yt to represent the difference between xt plus 1 and xt. And this is, again, just a simple linear regression problem. And we can solve it the same way as we did for reservoir computers. So there's a few key differences between NGRC and reservoir computers. First is that now because we got rid of the reservoir, it is more data efficient. And it is especially efficient in terms of the need for warm-up data. So in reservoir computers, usually you need to drive it for, say, by, say, several hundred data points to warm up the reservoir. But here, all you need is the number of delay states you have in the system. If your delay states is k equal to 2, then you only need two warm-up points to have the NGRC to start making autonomous predictions. So yes, so no more warm-up problem. And we have fewer hyperparameters to tune. And NGRC is generally considered relatively robust to the choice of nonlinear features. In particular, people have demonstrated good performance of NGRC just using simple quadratic nonlinearity shown here. So how does it do for the magnetic pendulum system? Okay, so here we test 3 different classes of nonlinear features. So first, of course, we're just using a bunch of polynomials up to a certain degree. And this is assuming that we don't have any particular knowledge about the underlying system. So let's just use a generic polynomial feature library and see how it works. And the second class of model, we consider radial basis functions. Here, basically, we're assuming that we know this is a central Newtonian force problem, and we even assume that we know the kind of the scale and the shape of the force field. But we assume that we don't know anything about where are the magnets. So we don't know anything about the center, so we can just use a bunch of radial basis functions with random centers to try to approximate the underlying system. And finally, let's assume that we actually know it's a magnetic pendulum system, and we know exactly where the magnets are. So basically, we give the exact nonlinearity from the underlying system. So if we use the exact nonlinearity, then unsurprisingly, we can have really good prediction for the underlying basins. So this is a real system. This is the basins predicted by the NGRC. And here the black dots are where the predictions are wrong, and they all come from those really fractal-like regions of the basin. However, if we switch to a more generic radial basis function basis, even when we give it 1,000 different radial basis functions as a nonlinear feature library, it was able to predict the captures large basins in the middle, but it really struggles with the more intricate basins on the boundary. And then when we give it polynomials, the NGRC really becomes really unstable. So here, black actually means the model prediction diverges. So it was really hard to have NGRC make good predictions with those generic features such as polynomials and radial basis functions. And of course, another interesting thing is that when we give it the exact nonlinearity, NGRC actually have very, very good generalization performance. So even when we only train on a single trajectory, so it only sees only phase space connected to one of the basins, it was able to predict all three basins really, really well. Whereas for genetic features, it struggles even with abundant data and many more features in the system. So then the natural question would be, how precise do we need those nonlinear features to be, or how close our nonlinear features have to be to the true nonlinearity in order to have a good prediction of those basins, right? So here, I'm showing basically the error rate, which is how often is your basin prediction wrong versus uncertainty in the nonlinearity, which means I give you the exact nonlinearity, but I perturb the coordinates of the magnets slightly, which is measured by this nonlinearity uncertainty magnitude. So here, for example, this 10 to the minus 2 uncertainty basically means I have, say, 1% uncertainty in terms of the coordinates of my magnets. So you can see, of course, when the uncertainty is very small, then it gets a very good prediction. By the way, I'm just labeling, say, 45% error rate, below which is, say, useful prediction. It gives like qualitatively similar basins as original system, whereas 60% is basically a random guess. So you can see that as we increase the uncertainty in our exact nonlinearity, the performance actually deteriorates very fast. So you can see that even with 1% uncertainty in the coordinates of the magnets, the NGRC already gives you a basin that's very different from the original system. And if you give it 10% uncertainty, then it just fails completely. So then you might say, well, are you being fair? Because maybe the magnetic pendulum system is just too hard to predict for any machine learning method. So just to test that, we can actually compare the original system where we perturb the coordinates of the magnets and see how does the basin change, and compare it to the NGRC with perturbed exact nonlinearity. So you can see that with 1% perturbation in the coordinates, the basins in the original equations doesn't change much, at least in like visually. Whereas the NGRC prediction already changed a lot. And even for 10%, you would have to really look to see the difference from the original basin, whereas NGRC already predicts a very different basin structure. Okay, now let's just maybe look at a few example trajectories and see, what happens when the basin prediction goes wrong, right? So here I'm showing it for NGRC using radial basis functions. So again, here the training fit is always good. So doesn't matter which nonlinear features you use, NGRC is always, if you give it enough features, NGRC is always be able to have very, very small training error. But of course, when you make predictions, things can go wrong. And I think, so if you look closely, the NGRC and the real system, the trajectory actually are close for a little bit, but then it diverges from each other, very similar to what happens in the, say, chaotic Lorentz systems. So I think this is one thing that makes basin predictions really hard. So because, say, in a chaotic Lorentz system, even when your short-term predictions fail, very often reservoir computers can still capture the long time climate of the chaotic attractor. But here, in able to capture the long time climate, meaning predicting the correct magnet the system would go to, you actually need to make very good, very precise short-term predictions, because otherwise you would diverge during the transient and you are very likely to make a wrong prediction. And of course, even when the basin prediction is right, when the NGRC and the original system actually goes to the same magnet, there could be mismatched transient in the prediction. Okay, this is the first part about the trade-off between RC and NGRC. Basically, we're showing that for traditional reservoir computers, it can do very, very well, but it generally needs more data. Whereas for NGRC, it needs much less data, but we need to choose our nonlinear features much more carefully, because other inductive bias we need to build in NGRC. So here I want to use the remaining of maybe 15, 20 minutes to just show maybe some fun, small thing we are looking at right now. Basically, there are cases in which, at least for NGRC, you need to be very careful, even when you have a very abundant data and perfect nonlinearity in NGRC. So this is a basic phenomenon. The exact same setup as the first part. So we have NGRC, and we are equipping it with the exact nonlinearity for the magnetic pendulum system. And we give it different amount of training data measured by the number of training trajectories here. And we ask it to predict the basin structure. And we measure the performance using the error rate P, basically, how often you predict a wrong basin for an initial condition. Okay, so what you can see here is that different curves corresponds to different regularization strengths in the NGRC. So if you follow one of the curves, no matter what is the level of regularization, you will see that as we increase the amount of training data, the NGRC would have better and better predictions. It would have a basin prediction that really resembles the original system. But suddenly, at some point, when you give it too much training data, it suddenly becomes unstable and just all the predictions diverge. So in this sense, for NGRC, more data can hurt even when there's no noise and there's no missing measurements, there's no partial measurements whatsoever. So we want to understand what's going on, what is causing this instability in NGRC. So I don't know about you, but my first guess was that, did NGRC somehow overfit the flow map, right? Because, a flow map is all you need to kind of propagate the dynamics and predict a dynamical system, basically. So here, flow map is defined as, this map that you take in the current state of the system and you map to the state of the system delta t times later. And we can also define the flow surface basically being the change you need to make to go from xt to xt plus 1. So we can look at how well does our NGRC fit the flow map. The guess was that, because we're only fitting the flow map on a finite number of data points, could it happen, just as in, say, regression using polynomials, we could fit those data points perfectly, but maybe there's some kind of very pathological oscillation between the data points that would make us deviate from the true flow map. So here we are just measuring the mismatch between the flow surface of the ground truth system and the flow surface discovered by NGRC. And as you can see, as we increase the number of training trajectories, or as we increase the amount of training data, there's no indication of overfitting whatsoever. The mismatch between the flow surface is always decreasing monotonically. So it seems that it is not the flow map that is a problem. So here we're just showing it for, just to show its generality, we're showing it for NGRC, not with exact nonlinearity, but with 1,000 different random radial basis functions. So you can see that with 100 training trajectories, the flow surface is not perfect. It's close, but not perfect. But NGRC was still able to predict the basins relatively well with an error rate around 20%. However, if you train with 1,000 training trajectories, well, the flow map now it's almost perfect compared to the ground truth. But the model somehow became unstable, and all the predictions diverge, and we didn't get a basin prediction at all. So, then what went wrong if flow surface or flow map is not the problem, right? So I want to show it from two different perspectives. One is from an integrated perspective, and one is from a more geometric perspective. So from an integrated perspective, the basic idea is that, NGRC, because it's trying to approximate a flow map, it's actually very nice to compare it with some traditional numerical integration schemes. So here we are using the linear multi-step methods, which is basically, you want to predict the next step, basically y sub n plus s using s previous steps and derivatives. Here, if bs is 0, it means we're not using information about derivative at the future step, so it is an explicit method. Whereas if bs is non-zero, then we are using derivative from the future, so it becomes an implicit method. Now, which methods from the linear multi-step method would be most close to the NGRC architecture, right? First, we know it doesn't use any information from the future, so bs equal to 0 is an implicit method. It's an explicit method. And again, it only uses the current state of the system. It doesn't use previous states. So it basically means a sub s minus 1 is minus 1, and all the other A coefficient is 0. And this method is basically the famous popular Adams-Bash force method. And I shall point out that NGRC is not a special case of those linear multistable methods because NGRC has more freedom in choosing the coefficients for individual terms in the update. So it is not constrained by the right-hand side of the ODE. So now let's just make an explicit comparison, right? So let's choose K equal to 2, which is we use the current state and one delay state in NGRC. And we compare it to the two-step Adams-Bash force method, which is shown here. You use the current state, and you use derivatives from the current state and from the current time step and one time step before. And the optimal assignment of the coefficient will be you would assign 3/2 to the current derivative, and you would assign minus 1/2 to the delay state. Now, if NGRC were to discover two-step Adams-Bash force method for the magnetic pendulum, how would the coefficients of the output matrix look like? Here, I'm just rewriting the pendulum equation all in first order, so it's easier to see what the coefficient should be. Here are the value of the natural frequency and the dissipation we're using. So this is basically what the two-step Adams-Bash force method would assign to the output matrix if it is written in the NGRC language. For example, the derivative of x, it depends on Vx. And Vx, the coefficient is 1. So we assign 1.5 to the current state of Vx, and we assign minus 1/2 to the delay state of Vx, and the same for all the other coefficients. Now, so what does NGRC actually discover? Here we're showing the coefficients for the output matrix of NGRC for 10 training trajectories, 100 training trajectories, and 1,000 training trajectories. So there are a few interesting things to notice. First is that here for Adams-Bash force, the optimal assignment is basically the split will be 3 to -1. So NGRC, on the other hand, likes to split things equally. So it assigns equal weights to the current state and delay state. But for nonlinear features, NGRC actually managed to get the split right. So the split is actually 1 to 3 for the nonlinear features. However, you can see that it confuses the current state with the delay state. So instead of 3, 3, instead of 3, 3, 3 for the current state and -1, -1, -1 for the delay state, sometimes it assigns -1 for the current state and 3 for the delay state. But the most striking difference is here highlighted in red and blue. So you can see here that NGRC splits the coefficients for the current state and delay state much more unequally. Or in other words, it gives much larger coefficients for both the current state and delay state, but with an opposite sign. If you sum up the two red coefficients here, it's actually the correct sum. It's minus 0.2, which is the same as in the Adams-Bash force method, but it just have this unbalanced split between the current state and delay state, which grows larger and larger as we give it more training data, which eventually makes the NGRC unstable as an integrator. So this is just showing the condition number for the output matrix, which actually grows rapidly with the number of training trajectory and becomes unstable at some point. So we can also see this from a more geometric perspective, because, you could be asking, well, isn't the flow map all we need to predict the dynamical system, right? Where does this integrator comes in, What's the difference between overfitting an integrator and overfitting a flow map? So here, one thing to realize is that for NGRC that includes delay states in its nonlinear features, it is a higher dimensional system than the original system being learned. So for example, the real flow surface for the pendulum system is from R4 to R4, whereas the NGRC flow surface is actually from R4K to R4, K being the number of time steps you look back in your nonlinear features. And during training, all the data we get is from this lower dimensional submanifold of the original flow surface, of the original flow surface. And it turns out when you try to fit too much data on this lower dimensional submanifold, it inevitably creates those transverse instabilities in the other directions. So here, just showing it graphically, if it's a stable NGRC, it would remain close to the low dimensional flow surface of the original system as it makes autonomous prediction. Whereas for an unstable NGRC, due to its transverse instability, it will diverge quickly from the flow surface. Then after that, it doesn't matter how well did the NGRC fit the flow surface, because you are never gonna see it. This is just showing the distance from the NGRC state to the flow surface as it makes autonomous predictions. And as you can see, the divergence from the flow surface coincides exactly to when NGRC becomes unstable. And is there an easy way to fix this data-induced instability for NGRC? Actually, it's there's an embarrassingly simple fix. So all we need to do is to look at the loss function for the ridge regression we're doing. So here, the first term is basically the fitting error, how close do we fit the training data? And the second term is the L2 regularization term. So one thing that's very easy to realize is that as you increase the amount of training data here, say as you increase the number of training trajectories, assuming each training trajectory gives you roughly the same fitting arrows, then it's easy to see that as you give it more and more training trajectory, this term would become more and more dominant, which would effectively decrease the regularization strength here. So when you give it too much training data, the system effectively becomes under-regularized and eventually becomes unstable. So, in order to maintain a roughly constant model complexity, which, measured by the Frobenius norm of the output matrix here, then the regularization strength should really increase linearly with the amount of training data. So we can actually just slightly modify our loss function to scale our regularization strength with the number of training trajectory in our system. And once we do that, we can do the same experiments on the same system, and then you will see that there's no more instability transition as we introduce more training trajectories. So if your initial regularization strength is good, then your performance would get better and better, and then it would saturate at some point, but it wouldn't lose stability as we give it more training data. The same for the condition number, and also the same for the mismatch for the flow surface. So the arrow for fitting the flow surface will no longer keep going down indefinitely, but it would saturate at a certain level as we introduce more and more training data. But of course, you don't want to fit the flow surface too exactly by using too small a lambda, because then the NGRC would be unstable. So with that, I think that's all I got. Happy to answer any questions or just have a discussion.
Yeah, thank you very much. Thank you. Any questions? Yeah, please go ahead. You can unmute. Yeah, thank you.
Okay, thank you for the nice presentation. I wanted to know what is the really difference between NGRS, the next generation reservoir computing, and the reservoir computing. I didn't get you very well when you were explaining.
Right. Yes. Yes, I probably went through too fast there. So, honestly, I was think that NGRC is a very different architecture from the traditional reservoir computer. That's why it has such a difference in terms of how much warm-up data it needs, how much training data it needs. So what I would say NGRC is much closer to those other methods that are based on predefining nonlinear features to make predictions. So it's very close to, if you're familiar, techniques such as Cindy or NVAR. So for example, in Cindy, you pre-specify a nonlinear function library, and you want to approximate the right-hand side of the differential equation using those nonlinear features. And for NGRC, it basically, is the basic idea is also to define a set of nonlinear features, and you want to use those nonlinear features to approximate the flow map. So it is a discrete formulation instead of the continuous formulation in Cindy. And the other two key differences is that in NGRC, you usually want to include delay states in your nonlinear features because you are trying to do the work of the numerical integrator as well. So you need some delay states. Whereas in Cindy, you usually don't include delay states. And also Cindy cares much more about sparsity and interpretability than NGRC. In NGRC, you can throw in 1,000 of features. You only care about predicting the dynamics well. So I don't know whether that answers your question or gives you a better intuition about what NGRC actually does.
Okay, thank you. Yeah, it's okay. I wanted also to ask about what is the complexity of NGC, or with respect maybe to the dimension of input data.
What is the complexity of NGRC?
Yeah, but if for example you have large input data, so how does it perform with respect to large input data?
Okay, so of course, how much computation you need for NGRC really depends on how much nonlinear features you give it. But in general, I think it's really efficient in terms of how much training data it can handle, because all you need to do during training is to perform this ridge regression, which can be really efficient.
Okay.
I also have a question, which is kind of getting us a better feel for the background for the NGRC. And so if I've gotten the right impression from the presentation, it seems like it's challenging to apply it for the problem you were working on with the magnets and the pendula. But can you give some examples of applications where it would be a very well-suited approach? And I can get the comparison to Cindy, by the way, was really, really helpful. So that kind of gives me already some insights, but I'd be curious if you could just comment on what have been some of the best success stories for the NGRC.
Right. So there are a lot of success stories of NGRC, especially actually. So I was kind of criticizing the use of quadratic nonlinearity in NGRC a little bit, but it actually is a very, very good inductive bias. First, because a lot of nonlinearities in the real system is quadratic. And I think there are some studies, showing some success examples applying to NGRC with quadratic nonlinearity to systems that has non-quadratic nonlinearity. So I would say, if you have low amount of data, you have low computational budget, NGRC with a quadratic nonlinearity is a really good starting point to try. But I think it's still an open question in terms of when does NGRC with quadratic nonlinearity successful and when does it fail? And I think just maybe one example I heard from people is that they actually had some success applying NGRC with quadratic nonlinearity to simulate the dynamics of jet engine even. So I think it's still an open question. So Andrew, you have a question?
Yeah, I have another one.
Yeah, sorry, that's Andrew who has been trying to yeah, do you want to ask your question, Andrew? Yeah. Andrew, are you there? Yeah, okay, he's not here, I think. Yeah, so okay, so Reagan, did you have another question or?
Yes, I got. Yeah.
Yeah, okay.
I wanted to ask, can NGRC also predict financial time series?
Sorry, say it again. Also predict what?
Financial time series, like stock.
I'm not aware of people trying that. I think for financial time series, I think a more appropriate framework would be, those methods that learn stochastic dynamical systems or differential equations than deterministic ones. NGRC is more geared towards deterministic dynamical systems. So I think people try that.
Okay, thanks. Because you were talking about nonlinearity, and usually financial time series is also is generated by a nonlinear system, which is affected by a lot of parameters. So we consider it as a nonlinear source that can generate financial time series. That's why I asked this question. Okay, so because of the stochasticity, okay, you're right. So okay, thanks.
Okay, Mohammed, do you want to talk?
Thank you for the talk. So I wanted to ask about the choice of features. Do you think if someone say used like Fourier features, would there be like an improvement in performance?
Sorry, say the question again.
So I was saying, would it be better if someone say use Fourier features, or maybe some other basis type features, would that give a better performance?
If someone uses Fourier basis functions for NGRC. Yeah, so we haven't tried that for the pendulum system, but actually we actually tested NGRC on a much higher dimensional dynamical system, which is basically the so-called coupled core model oscillators. And there the underlying nonlinearity is actually the sine function. But and we tested the some variants of the Fourier basis functions for NGRC. But I think so. So in the core model system, the nonlinearity is sine of theta I minus theta j, theta I and theta j being the phases of the ith oscillator and jth oscillator. So if you only give the NGRC a Fourier CRSC, say in terms of sine of k theta, it doesn't do well at all. But of course, if you give it the exact nonlinearity with phase difference, then it does well. So I think it also really depends on how, even for Fourier basis function, it depends on how well it matches the exact nonlinearity in the underlying system.
All right, okay, thank you.
Yeah,
Hi,
Andrew? Yeah.
hi, sorry, does my microphone work now?
Yeah, it is working. Yeah.
Okay, great. Sorry about the issues. So thank you for the nice talk. I was wondering, could you go back a couple of slides to so my question was, you have, say, a system which has 3 fixed points,
Right.
and how do you train the reservoir? Do you have a trajectory whereby you start in some initial condition and then you go to a fixed point? But how does the reservoir computer become multistable? And how do you relate the points in the original basins picture to, like, is it a projection of basins of attraction in the reservoir system, or is it a different kind of method you use to reconstruct the basins of attraction?
Mm-hmm. Are you asking more about the traditional reservoir computer or the NGRC?
Yeah, let's go with the traditional, but I guess the question still applies to both.
Right. So so for the traditional reservoir computer, what we are showing here, it's actually the reservoir computer is only trained with one initial condition, and we are also asking after training, we're also asking the reservoir computer to predict from that exact same initial condition. For NGRC, it's actually very simple to train with multiple trajectories, right? It's let me see if I can find. So yeah, so it's basically you have each individual trajectory, right? So you basically you can stitch them together, and it's always trying to predict from the current state to the next state. It just that you exclude the final point from one trajectory, and you don't ask it to predict using the final point of that trajectory to predict the first point of the next trajectory.
Yeah, so I was wondering how, like you mentioned, how many trajectories do you show? So does that mean, say, do you train the reservoir based on trajectories from 10 different initial conditions? And then do you concatenate? So does your Y matrix and G matrix, are they composed of smaller matrices of each the same amount of training points, is it?
Right. Yes.
So that's what you do, is it?
Yeah. So yes.
So in this case, Y1 would be the trajectory taken from initial condition 1. But small y, the letter small lowercase y, is actually a matrix itself.
Okay, so Y1 would be, say, from the first trajectory, you go from t equal to 1 to t equal to 2, and Y2 would be, still in the first trajectory, you go from t equal to 2 to equal to 3, and at some point here, you would exhaust the data from your first trajectory, and then you go to the second trajectory. So say Y.
Okay, this makes sense. So what you could say is that if you trained on only one trajectory, your big Y would just be, say, data points in a time series, right?
Right.
But then if you train on multiple trajectories, your big Y consists of many kind of sub-intervals, right? So that's what I was wondering. Okay, so then this makes sense. But then when you start your trained system from an initial condition, that initial condition, how does that relate to the initial condition in the original system?
Right.
And
Okay.
then do you project, you run the system until it reaches a fixed point and you project that fixed point down, and that's what you show in your reconstructed basins pictures.
Right. So I think, okay, the question may be, I think it sounds like connected to your previous question, where do other initial conditions for training trajectory come from, and where do we do the prediction, right? So let me see. There's okay, maybe. So okay, so this is basically the kind of the square of the state space that we are focusing on. So this is x0 from certain range, y0 from certain range on the table, basically. So here to train NGRC, or I think similar if we want to train traditional reservoir computer, you pick, I think here we used 100 different initial conditions. For each different initial condition, you generate a time series, until it converges to one of the fixed points. And you use those 100 trajectories to train RC or NGRC. And then, during prediction, then we pick a random initial condition inside this region, which does not necessarily come from the training initial conditions. And then we ask, so for example, for NGRC, because it only needs a field warm-up data, so we run the ground truth equation for 2 or 3 steps to generate those warm-up data. Then we can just add the NGRC to make autonomous predictions. For reservoir computer, for each new initial condition to predict, you need a much longer warm-up data, which in our case, we get from the ground truth equation.
Yeah, that all makes sense. But so then in terms of like the distribution of like, so did you try to see what would happen if you chose, say, so in your real picture, you have like 100,000 different initial conditions plotted, right? So when you showed your number of trajectories, did you then say pick every single point you could to then check, did you get the right point in the end when you trained the system?
Okay, so during training, right, it's all the initial conditions are sampled uniformly in this region, whether it's 100, 10, 1,000, 10,000. And during prediction, so to get this basin map, right? So we are just doing a uniform grade on this region. So be like 300 times 300 grade, and for each initial condition on this grade, we run the, say, RC or NGRC until it converges, and then we look at the prediction, and we identify which of the magnets the NGRC think it converged to, and that's how we got this map.
Yep, gotcha. Cheers.
Okay.
Thanks. Ankita, are you still here? Did you want to ask your question? There are some things on the chat. Do you want to go over them, or? There are 2 comments.
Right. Okay. Let's see. I guess the normal matrix in your matrix inversion consumes some computing when scaling to high dimension. Yes. Yeah, that's right. But I think it, like, regardless, it's much, so those are convex optimization, and they are much more efficient than the gradient descent we're doing for neural networks, for sure. What would be some possible application areas for NGRC? I think one example I mentioned that people were looking at would be, you know, those predicting the dynamics of jet engines. I think Dan Gauthier from Ohio State was also, you know, trying to apply NGRC to the control of drones and autonomous vehicles. So that's another area. Yeah, so those are the things I have seen.
All right. Yeah, thanks. Any other comments or questions?
Hello.
Yes, I have two. One is technical, one is more philosophical. I'll start with the technical. The more data that is noise-free, you say it's a problem, right?
Right. Well, if you don't recognize well.
So the thing is, and you treat it with the regulator term, and if you increase it, somehow things get better. So I'm wondering, and it's not for the first time, what would be the competition between the regulator term and the noise term? The other question that I have is, as much as this methodology is very impressive and you presented it very well, I'm still wondering about, you know, dynamical systems is starting from physics and going to other branches of science, but the new physics, can you believe that you can predict the new physics? For example, Feynman path integral or the diagrams, could they be predicted if we didn't know them a priori?
Right, okay. Great questions. For the first one, I think you were asking about kind of the interplay between noise and regularization. So what I think is that noise very often in this context can also act as another form of regularization. So actually, one thing we're thinking about right now is that, you know, instead of increasing the regularization with the amount of training data, another thing you could do is that you could artificially introduce noise into your training data. This would also help to regularize your model, and perhaps you can get away with just a constant level of noise in your training data to sufficiently regularize your model without, regardless of how much data you have, because you know you have noise in all your data. For your second question, okay, it's just my personal opinion, but I think those machine learning methods, they are all just one of the tools we have, you know, in a vast toolbox. They can certainly be very, very helpful to help us make sense of data. For example, I think many of those methods have been applied to, say, biological data, try to get some insight about, say, cell division or things like that. in terms of discovering new physics, I think as far as I can see, or at least with the current technology, you need combining both, so, like it's
So the human intuition and the ingenuity is not replaceable so far.
not yet.
Okay.
Yeah.
Okay. About the first point, I accept gladly your answer, but I have a question. At the very beginning of machine learning, people say the more data, the better.
Mm-hmm.
And now, the more data, we have to regulate it. So this is a bit of more artificial than intelligent.
Okay, so, well, a few things. First, there's also the phenomenon that more data can hurt also appears in deep neural networks. That is in connection with a phenomenon called double descent. So that's another different story. But here the story is simpler. It's just because you need better regularization. And I think that also is a big difference between, machine learning for dynamical systems and machine learning in general, right? Because for machine learning dynamic systems, you really need to worry about stability. It's not enough to just fit a high dimensional surface well, which is many of the neural networks are trying to do. Here, aside from fitting the flow map well, because you need to make those autonomous predictions well into the future, you need to care about whether you can stay on that flow surface, which
in other words, you want me to converge and not become chaotic.
In a sense, right? You want to stay close to where the interesting dynamics are. You want to stay where your data are coming from, and yeah, like.
Hello?
Yeah, go ahead. Yeah.
Yeah, okay. I enjoyed the talk and the answers, and thank you so much.
No,
All right, thank you. Yeah, thank you. Other last question, comment? I think that I saw someone else, but I forgot who.
Yeah, if we can ask one.
Yeah, go ahead. Yeah, I think I saw you.
Okay. Yeah, thanks very much. Thanks, Yuanzhao, for the very insightful talk. It's really interesting. My question would be, how do you figure out the n in your regularization term lambda n? Do you think is there any other possibility like square root n or log n, something like that?
So you're talking about this regularization coefficient?
Yes. So if you look at your second equation, you've got like a linear to number of data points. So how do you figure out like why is linear, why is not a log n or square root n, that kind of thing?
Okay, so you're talking about this term, right? So
yes,
why linear is the right scaling? Yeah, so I think the intuition is that if you look at the first term, which is basically the fitting arrow, right? Here, if I make the assumption, each individual training trajectory contribute a similar fitting arrow. So then what happens when you increase the number of training trajectories? This fitting arrow term would increase linearly with the number of training trajectories. So to counteract that, assuming that we want to keep the norm of the training matrix roughly constant, what we need to do is to also increase the regularization strength linearly. So that's the thinking for the linear.
Yeah, that makes sense. Maybe a further comment on your previous like little y, that kind of thing. I guess it's a regression formula, which is the G times the G transpose thing.
Right. yeah, it's basically this.
Yeah, it's
It's-
a regression. Yeah. Yeah, you elaborated. You concatenate like different dimensions. Maybe you can just make it like a multivariate regression, which means each little y is a vector, that kind of thing. Maybe it can, hopefully it can make more sense. I don't know.
Yes, training on each trajectory individually.
Cross section, yeah.
Yeah.
Yeah, I don't know. But anyway, yeah, really good talk. Thanks very much.
Yeah, thank you.
All right. Yeah, thank you very much. So let's thank the speaker again. Thank you very much, and see you soon. Yeah. Bye-bye.
Thanks for organizing.
Yeah, thanks. Bye.